Let's look at two-dimensional motion where we have an initial velocity that is at an angle. When we have this, we have it set up like this. We have some initial velocity and we have some angle. And different questions might ask you different things in the way that that might be set up. But let's talk about a few things that we know. First of all, we know at the top that our time is equal to half of the total time if it is taking off and landing at the same height. We also know at the top that our velocity in the y direction at the top is going to be 0. Still the same idea as what happens as when we throw a ball up in the air and catch it. So if a ball goes up and down and we catch it at the same height, it goes up for half the time and comes down for the other half of the time. If we talk about our total time, we have our total time that would go from here to here. We would have some displacement in the x direction that would go across. At the very end, our displacement in the y direction is equal to 0 because it's gone up and it's come back down. We have our total time across there. And the displacement in the x direction goes that way. The other thing that we know about this point here is that our initial velocity in the x direction remains constant. So our final velocity in the x direction is the same. And we know that whatever's coming down here is the same amount of whatever's going up there. If we look at our throw here, which is our initial velocity of u, we can break that into what's happening in the x direction and in the y direction. We know our angle here. We can have our x direction, which is coming this way, and our y direction, which is going up this way. And if we look at the way that our triangles go, we can say that u in the x direction, let's label these, u in the x, u in the y direction. U in the x direction, so right here, is the direction that is adjacent to the angle. So we can say u in the x direction is equal to u cosine of theta, and u, our initial velocity in the y direction, is equal to u sine theta. So that can give us information to put into our XY chart. When we set up the XY chart, there's a few things that are known here. First of all, we don't have any acceleration in the x direction. There's nothing that is pushing it forward or pushing it back that would change that velocity as it travels through the air. For the speeds that we'll generally be going, air resistance isn't going to be enough to be a measurable difference. In the y direction before, when we were just focusing on a drop, we said that our gravity, our acceleration due to gravity, is 9.81 meters per second squared. Here in this situation, we'll have a negative in front of it, just like we did when we throw a ball up in the air and catch it. Gravity is always going to be pulling to the ground. And with gravity pulling to the ground, we keep that as negative. That means that if the velocity is going up, it's positive, and if the velocity is going down, it's also negative. Anything that is going up is positive, anything that is going down is negative here. We can put our initial velocities in here. So in the x direction, our u is equal to u cosine of theta. And in our y direction, u sine theta. Other things that we know here, we know that because there is not an acceleration in the x direction, we can say that our final velocity is also u cosine of theta. Sometimes that's helpful, most of the time it's not. The other thing we still know is that we have our bridge in our time. Sometimes we have enough information in one of these directions to solve for time, and we can put it in there and solve it like we did when we were looking at a ball that's kicked off with no vertical velocity. Sometimes it gets a little bit messier. But we have to keep in mind that these times are the same, and so we can use that to drive whatever process we need to take. We want to keep in mind the principles that allow us to make these calculations. In the x direction, we don't have any acceleration, so we have a constant velocity here, and in the y direction, it travels just as if we'd throw it up and catch it, because gravity doesn't care that it's also moving to the side. Let's do an example here. Let's say we have a situation here where we have something that's being tossed at 15 meters per second at an angle of 33 degrees, and we want to know where it lands. So the first thing we'll do is we'll set up our XY chart. In the X direction, our acceleration is always 0. In the Y direction, because it's going both up and down, our acceleration is negative 9.81 meters per second squared. In this situation, we're given our initial velocity of u, and we know our angle here. And so when we set this up in our XY, with our XYs, we have in the X direction here, we have u cosine of theta. So we'll have 15 cosine of 33. And in our Y direction, what's going up and down, we have u sine theta. So we have 15 sine of 33. So we know that for this throw that's happening here. We're going to do two things. We know that our object is going to land at the same height at which it was tossed from. So what that means is over here in the Y direction, our velocity will be opposite what we have here. So negative 15 times the sine of 33. And in this situation, we know our initial velocity, we know our final velocity, and then we know our acceleration of negative 9.81 meters per second squared. So we can use that information to solve for time. We'll use equation 1, v equals u plus at, because we know those variables and we're solving for t. We'll rearrange it to solve for t. We'll subtract u from both sides and divide by a. That will give us that our time is equal to v minus u over a. We know these things. Our v is negative 15 times the sine of 33. We're going to subtract 15 sine of 33. That does not cancel. You're taking a negative minus a negative, so it'll be double that. And then divided by negative 9.81 meters per second squared. When you calculate that out, you'll get your time is 1.665 and a bunch of other decimals. We're going to put that at 2 sig figs of 1.7 seconds. In the second part, now we know how long it's taken for it to travel that distance. We focused on the Y direction. It took 1.7 seconds for it to go up at this velocity, come down at that velocity, based on that acceleration. So now we can put it in here. We say, well, now our time is 1.7 seconds, 1.7 seconds there also. Now we have enough information in the X direction to solve for the displacement in the X direction. So we'll do that next. We can use the equation, shift this a second, S equals ut plus 1/2 at squared. The nice thing about the X direction is that our acceleration is equal to 0. That means 0 times anything is 0, we get rid of this whole thing. So we just have that our displacement is our u, our initial velocity, times our time. And we know that in this situation, our displacement is 15 cosine of 33. It's our u in the X direction, and our time is what we got here of 1.7 seconds. And when we multiply those two things together, our displacement here is 21.386 with a bunch of other numbers. We're gonna bring that to 2 sig figs. So we just have 21 meters. So in this situation, we were able to take, based on what we know, we were able to take and set up something to get us time in the Y direction. That time carries over into the X direction, and we're able to use that to solve for our displacement in the X direction. This example is similar to the one before it, except now we're going to have the Y have a number and it's not going to be 0. So before we had it landing at a flat spot, now we're looking at it's landing somewhere above or below the point that would be flat. This gets a little bit goofy because means that we need to use the quadratic equation to solve for time. But here's the scenario. We have a 25-degree angle with an initial velocity of 42.0 meters per second. And it's going to travel up, and on its way down, it's going to hit some wall that's some distance away. And that's what we're going to find in the x direction. So we'll be looking for s in the x direction. Let's put in the information we know. From this, in the y direction, we know it lands 4 meters above where it had originally been launched. So our displacement in the x direction, or in the y direction, is 4.0 meters. We know that our initial velocity, we can break that down to u cosine of theta here. So for x, we have our u is 42.0. I'm going to write 42 cosine of 25. We are going to keep 3 sig figs in these, but it doesn't fit very well here. 42 sine of 25 here. And we also know our our acceleration in the x direction is 0, and our acceleration in the y direction is negative 9.81 meters per second squared. We still have enough information in the y direction to solve for time, but this time we have s, u, and a. None of them are 0, so it makes it a little bit more complicated. So we'll set it up in the y direction. S equals ut plus 1/2 at squared. And when we put our numbers in there, it looks like this. Our s is 4.0. Our u in the y direction is 45 sine of 25 times our t plus 1/2 times negative 9.81 times t squared. That's sort of a big mess of stuff. What I'm going to do is 2 things. One, I'm going to move this 4 over here by subtracting by 4. And 2, I'm going to put it into the format that we would use for the quadratic equation. So when I do that, that gives me 0 equals 1/2 times negative 9.81 t squared gives me negative 4.9 t squared, plus when I calculate this, the 45 sine of 25, I can get a number. It's going to be 17.7 t. I'll keep it at 3 sig figs here. And then I have minus 4.0 because I took that and subtracted it to both sides here. This allows me to get into quadratic equation formula. So now when I use the quadratic equation, it's going to give me 2 numbers. Those 2 numbers are 3.37 and 0.242. Now, if we go back to the beginning here, we're going up and we're coming down. So there's 2 points where we're going to get a displacement that has a time that allows this to happen. So our displacement is at 4 meters. Well, it also hits 4 meters right here. Based on the problem, though, it's coming down. So at 2.242 seconds, it's 4 meters going up, goes all the way up, comes back down, and now at 3.37 seconds, it's 4 meters, and it's on its way down. So this is the time that I'll use for the remainder of the problem. The second thing I'll do is in the x direction. And in the x direction, we can say s equals ut plus 1/2 at squared. X direction is delightful. Oops, can't see that. Let's try it again. In the x direction, I have s equals ut plus 1/2 at squared. And in the x direction, a is equal to 0, so we can take that off completely. And so we can say our initial velocity in the x direction is 42 cosine of 25. Again, we're keeping 3 sig figs. I only wrote 2 there. And then I'll take it times my time of 3.37 meters per second. And when I do that, I get 128 meters. That's brought down to 3 sig figs here. So 128 meters away is how far that would be. If we look back at our diagram to start here, we have it launched at a 25-degree angle going 42.0 meters per second. It's going to go up, it's going to come down, it's going to land on something that's 4.0 meters high, and that also happens to be 128 meters away. Example 3 is goofy. We have an unknown velocity of something that's shot at 40.0 degrees. It lands 72.0 meters away on a flat surface. When we set up our XY chart, we know that our acceleration in the X direction is equal to 0. Acceleration in the Y direction is negative 9.81 meters per second squared because it's going up and coming back down. We know our initial velocity in the X direction is u times cosine of theta, and in the Y is u times sine of theta. And because we're landing at the same height on its way back down, our final velocity in the Y direction will be negative u sine of theta, because it's the same velocity, it's just going in the opposite direction. The only other piece that we know is that it lands 72.0 meters away in the X direction. Now, I don't have enough information here to solve for time, and I don't have enough information here to solve for time. What we do know is that time is the same in both directions. So we need to use that along with what we do have to figure out what's going on. How does this look? Well, if we were to solve for time in the X direction, we would say S equals ut plus 1/2 at squared. And because in the X direction, a is equal to 0, that whole thing goes to 0. So we could say S equals ut. And to solve for time, we would just divide both sides by u. So time is displacement over u. Let's do that. We're going to say time equals, our displacement here is 72.0 meters over our initial velocity in the X direction, which is u cosine of 40.0 degrees. We know that. We can also do that in the Y direction. However, we won't use the same equation because in the Y direction we know our final velocity, our initial velocity, and the acceleration that we have. We're solving for time, so we can use equation 1. It's v equals u plus at. When we rearrange that for t, subtract u from both sides and divide by a, we get that t is equal to v minus u over a. And we have something to put in there for this. So we'll say our u is negative, or our v is negative u sine theta. We're going to take away our u, which is u sine theta, and then we'll divide by negative 9.81 meters per second squared. Well, we can do something with this. We're taking negative u sine theta minus another u sine theta. So in this situation, let's slide this up just a second. We'll have negative 2u sine, and theta here is 40.0 divided by negative 9.81 meters per second squared. Our negatives will cancel out. So in the Y direction, when we solve for time, we have 2u times the sine of 40.0 divided by 9.81. So now I know my time as I would solve for it using the information I have in the Y direction, my time as I would solve for it using my information in the X direction. So Y direction here, X direction there. Time is the same in both. So I'm going to set these two equations equal to each other. When I set these equations equal to each other, I'm only left with a single variable, and that variable is our initial velocity, just plain old u. Not in the X, not in the Y, it's just the one that we're looking for. So I get this mess here, and we're gonna do some kind of dirty math to get to where we need. First of all, we'll cross multiply. So I'm going to take 72.0 times 9.81. And I'm going to set that equal to what I cross multiply here, 2 u sine 40.0, that's from here, times what I have over here, u cosine 40.0. We're going to do some math here. I love some math. It's a heart. It's my heart. And stick it all in the calculators and we get 706 and is going to equal 0.985 u squared. From there, we can divide both sides by 0.985. Cancels out over there. The u squared comes because we have a u here and we have a u here. So when we're multiplying these things together, the 0.985 came from 2 times sine 40.0 times cosine 40.0. The u squared came from u times u. When we multiply that out and then take the 706 divided by that, we get u squared is equal to 717. And when we take the square root of both sides, we get that our initial velocity is equal to 26.8 meters per second. That is a really messy way to get to what we're looking for right here. However, it's taking the principle that we have a time that's the same in both of them, using what we do know about each situation to get to a variable that or an equation that has a single variable of u. When we get there, it's a bunch of dirty math in order to get to where we need to be. So what this tells us is that if something is shot off at 40 degrees and lands 72.0 meters away, it was shot with an initial velocity of 26.8 meters per second.